Yeah. It's a system. I don't know if it's the best system, but I got PDFs of which problems from exam 3 each of you missed. And of course it's nice. I could have printed out, one per page per student and handed it to you, but unfortunately they write on there which one you missed and what the correct answer is. And you're supposed to tell me that. So I made an Excel sheet and entered all of the ones that you missed by hand. I don't know. Took my wife's paper cutter, split these up. So now you should know what you got. If you're curious at your name, the first number is how many you got right out of 30. Like this one says 26 out of 30. Your percentage score, and then a negative number, -4. And then the 4 you missed. So I have posted on WebAssign under the resources where the syllabus and the superhero paper and the other exam solutions have been, the questions to exam 3. So you can see the test again. You know how you answered, and you know which ones you missed. So on a piece of paper this time, write if the first one you missed was number 4, write number 4, what you think the correct answer is, I don't remember, C, and then give me a brief explanation why. You know how my explanations are from exam solutions and homework? It doesn't have to be long, just I want to see that you understand it. And you only have to answer the ones you missed. And we'll turn that in Friday during class. So if you haven't gotten your stuff, you can come up and see what you got. And then again, just write down, I missed number 4, I think the answer is yada yada, and this is why. I missed number 7, I think the answer is this, and why. And if you get them all right, I'll give you half of the points you missed back on exam 3. And we'll have it due Friday. Questions? Yeah. Due Friday, that part? Sure. I'm confused now. I repeated it twice now, so I don't know which part you missed. Answer the ones you missed with a brief explanation. Write it on a piece of paper and turn it in Friday. And if you get them all right, I'll give you half points on the ones you get right. Back on exam 3. As for the superhero paper,
you said you wanted an email copy?
Yes, there's a hard copy and a digital copy.
You want that sent to your email?
My email on the syllabus would be ideal. But yeah.
Hey, my strip isn't in that. I took the test later because I had
Oh,
all that.
you're right. Did you get yours?
Yeah, I got my score sheet back. I can just
Do you have it? Do you have it here?
No, it's back in my dorm room.
Okay, that's right, because yours didn't go through the computer.
Okay, what I can do
So
is I can just check with a friend.
you can check with a friend or send me which ones you answered, and I can tell you which ones were
Okay.
wrong, because I checked yours right on the thingy.
Okay, cool.
So yeah, sorry about that.
Okay, it's all good. Thank you.
Wait, so you want the syllabus with it?
No, I was just saying my email's on the syllabus.
Oh, okay. So
Yeah, papers can go right here.
An extra copy of the test, or do we have to?
The exam 3's test questions are posted on WebAssign under the resources so that you can see all the questions. You may email me your digital copy of the superhero paper today, yes. I'll just email me by midnight. So you can come up and grab your thing or turn in your paper as I start lecturing. Yeah. I would prefer that I can access the words, but if all you can do is a PDF, I won't turn it down. Mainly because I don't have to count how many words you did then. A Word doc is great, yeah. PDF, if that's what you got, is fine. But if you're converting it just for my sake, please don't.
Wait, are we sending an email to you as well for this?
Yeah, and the instructions on the superhero paper are a hard copy and a digital copy to be turned in. Say again? To my email address, yeah, that's fine. Yeah, the one on the syllabus is best, but a lot of you have been emailing me through the university's email. I get both. I just check the one on the syllabus more often.
So should I turn in both the hardware and the digital for
Yes, you should turn in both the hard copy and a digital as the instructions require, yes. Sometime today, yes.
Is it okay if I did some correction?
Yeah, that's fine. Other questions? If they come, oh yeah. Yeah, I've been receiving lots of your emails. Thanks. Oh, okay. To bring it as soon as you can. Well, you know, I can print these. I just didn't want to be printing 80 of them. Yeah, if I have your digital copy by today, yeah, you can bring your hard copy Wednesday. I have to admit, I want one. I want one today to know you're done, for sure, because you've had all semester. If other questions come up, let me know. Obviously, everybody is not coming to class that took the test, so they're not going to find out about this. They'll just have less time, I guess. Looks like the majority showed up. Good. Excited to read them. Okay, so quick review. Get your clickers out. I'll ask a few questions about last lecture to review and see what stuck. All right, so we started electrostatics, learned about charges, which ones there are, whether they attract or repel, what that means, the forces between them. So let's see. A negative ion has more what? What does that mean? Polling's open, channel 44. Go for it. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. 74% think it's B, which is the correct answer. Good. Remember, atoms are made up of protons, positive charges, electrons, negative charges, and neutrons, which have no charge. If you remove some electrons, then the atom becomes net positive. If it gains electrons, it becomes net negative. Okay, then Coulombs Law describes the forces between charges. If we change the distance between these charges, what happens to that force? And as you answer, I'll remind that gravitational force, there's an attraction between two bodies that have mass. With Coulombs Law, we have opposite charges and same charges, so they can attract or repel. Either way, something happens if they get closer together. What? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. Half of you think it's B, but about a third of you think D. It is B. It increases. You get closer together, the force is going to increase. Whether they're the same charges and they want to repel, or opposite charges and they want to attract. The force is based on the quantity of charge and how close they are together. But that force can be attractive or repulsive for electrostatics, where gravity is just attractive. Say again? And either way, it's the same force. If you have plus and minus, same charge, they're going to attract or repel. Plus, minus. Positive and negative, do they attract or repel? They attract. Opposites attract. If I replace the negative with the positive so that they're both positive, same amounts of charge, they're going to repel with the same force that the other two attracted, because they're the same distance, same charge. Okay, one other aspect of Coulombs law. This one. How does distance affect it? You know, if they get closer, it increases the force. But how about a little more quantitative? What if they're twice as close? And again, this would be true whether they're positive or negative. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. And 2/3 think it's B. You are correct. Coulombs law is an inverse square law. I write it on the board at the moment, but the lights are off. Force is proportional to 1 over the distance squared. So if you cut the distance in half by a factor of 2, then the force is going to increase, that was the last question, but by a factor of 2 squared. And 2 squared is 4. And if you move them to be 4 times as close together, so that they're 4 times farther apart, what happens to the force? 4 times farther apart. 16. They increase the distance by a factor of 4, so the force goes up or down by a factor of 4 squared. 4 squared is 16. So the force decreases by a factor of 16 if you get it farther apart by a factor of 4. And I think I had one more I wanted to do. Yeah, this one. All right, pulling open. This is what happens in a thunderstorm. The with air drafts flying around, water molecules, water vapor, they rub into things. When they separate, some of them take charges with them. You get positive and negative charge buildup in a cloud. Clouds typically build up a negative charge on the bottom, positive on the top. So what happens to the ground below that cloud? That's what this one's asking. So you got this charged cloud moving over a section of ground. What's it do to the ground below it? If you're having trouble, remember my 2x4 or the balloon on the wall. That might help you. Ten, 9, 8, 7, 6, 5, 4, 3. Oh, we got one more than we ever got before. All right, 2, 1. Ooh, we're split. 44% A and 46% B. So you guys are split. This is great. This is fun. Because this is when you guys get to hash it out a little. So we got a cloud, negative on the top, positive on the bottom. And it comes over a section of ground. Thank you. Negatively charged on the bottom, positive on the top. Thank you. Hash it out. See if one of you has better reasoning skills and can convince your neighbor. I want to see which way this sways. There's a Coulomb force from both sides of the cloud, but distance matters. Polling is open. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Meh. Ooh, we got 3/4 of you thinking it's B now. So more of you switched to thinking it's positive than negative. Good, because that's the correct answer. The bottom of the cloud is, get it right, negative. The top is positive. They've separated charges in the cloud. If that comes over a section of ground, which part of the cloud is going to have more of an effect on the ground? The bottom, because it's closer. Both are going to exert forces on the charges in the ground, but the one on the bottom is closer and is going to dominate. Negatives on the bottom, and negative charges attract what? Positive. So it's going to polarize the ground and cause the positive charges to come up, and it's going to repel the negatives pointing away. So it actually has a net effect of making the ground below that cloud positive on the surface. Question away. The ground, by the acquiring, it already has charges in it. And most of the time it's neutral and balanced. So it's maybe a better way to word that would be acquires a net charge. It's kind of like the door in this case. This is like the cloud. I could charge it up. And the door has both charges in it. But it's going to get polarized. Before, we'd say, yeah, it's neutral, it has no charge. But if it gets polarized, we say it acquires a charge because they rearrange themselves so that it seems to be charged and it's attracted, just like the charges in the ground. Yes, yes. Yes, yes. And that's, okay, so he was thinking that the ground might be acquiring or taking charge from the cloud. And that is to help us review charging by conduction versus charging by induction. By direct contact, like what's happening in the cloud, there's charging by conduction. And they separate, charges separate. This acquired a net positive charge, and this acquired a net negative charge. Similar in the cloud, so that's how we got a separation of charge in the cloud. They're not in direct contact with the ground. And this can't touch all the charges in the wood either. So it polarizes the charges in the wood. There's a direct transfer of charge only from where it's making contact. But you remember with the electroscope, I can just bring it near it, and the wood can get polarized and acquire a charge. But not through direct transfer, through indirect transfer. Lightning strike would be a direct contact, yeah. And lightning has the effect of, the balloon's getting tired, isn't it? Would have the effect of, okay, there's a charge imbalance, and they want to balance back out. So if it strikes, now the charges can flow and balance themselves back out for a bit until charge builds up again, and they acquire more charge. Back here, you had a question?
Well, no, you answered it. I was going to ask if the ground actually acquires charge, but since it's polarizing, it does.
Yes. Yeah, polarizing is effectively becoming charged.
Because I read acquires as it steals electrons from the cloud, but it actually doesn't do that.
Okay. So, yeah, the terminology could be better in this question. Duly noted. Thank you. But do realize when something's polarized, it's as if it's charged. When I remove the balloon or the cloud moves on, the door and or the ground would go back to being neutral. The charges would rearrange back to being random. Not all, the positives pointing one way and the negatives pointing another. There's a question here.
So if the charge is on the bottom, or positive charge on the bottom of the cloud, would the ground have a negative charge?
Absolutely. If the charges on the cloud were flipped, then the ground would get charged the other way. Yeah, on the surface. There's one over here.
Yeah, just a quick question about thunderclouds. Is it implied that thunderclouds are polarized themselves, where usually one top half is one charge and then the bottom half is another?
Thunderclouds are generally polarized like this. The charges separate due to all the dust and water molecules rubbing against. And yes, one charge tends to accumulate on the top and the opposite on the bottom.
Okay, are you saying when they touch, they actually transfer to one another, but when they don't touch, they polarize?
Yes, when things touch, charge is free to transfer. If they're both insulators, the only charge that can transfer is where they're making contact. Because remember, charge over here can't flow through the insulator to get over here if they're insulators. So charge would only transfer by conduction through touch right where they're touching. If they're conductors, then as soon as they touch, any charge over here goes woohoo and can flow. And it's still transfer of charge by conduction. If they don't touch, they influence each other by the Coulomb force. They feel these charges, but they can't transfer directly. But you can polarize it and charge it indirectly. But if you remove it, it'll go back. Most things.
Can I ask a related question on the homework?
Homework question? Yes.
Okay, when the can is exposed to the negative rod,
So the metal can, negative rod.
but it doesn't touch, so that's going to
So-
polarize the can on
The-
that side with positive.
Yes, it will polarize the can with positives because the positives in the can are attracted to the negative of the rod.
Right, so then when your finger touches the opposite side, which is going to be negative,
So far, so good.
so then the can, it looks like you need to know whether the finger was a positive or a negative. More positive or negative.
The finger is essentially giving a path to ground so charges can flow on or off. So I'll finish it off for you. If this is negative, we bring it near the metal can, which is a conductor. The positives in the can start pointing which way? Towards it. The negatives that way. So if with that near it, I come in and touch here, then the negatives can flow off, leaving the can with a deficit of negative charge, meaning it'll get charged positive.
Okay, does that have anything to do with the same body that's holding the rod, touches it on the other side? Does that have anything to do
The fact that it's me? Somebody briefly mentioned it last time. True, where I'm touching here, whatever charges are on there can flow through me, but only those charges. And now that I've held it a while, we've come to equilibrium. I'm touching ground. I've neutralized again. Any charge on here can't flow through me because this is an insulator. So it's immaterial in this case. So a shortcut, if this is negative and I touch it, that's charging by conduction, and this becomes the same charge as this. By indirect transfer is charging by induction. Negative, bring it near, do that little thing, and that'll get charged opposite of what this was by induction. Charging by conduction will be the same charge. Charging by induction, the thing gets charged oppositely. So if this comes in negative, and I do that, that'll become positive. If this were positive, that would become negative through induction.
Why does it do that?
Well, again, because if this is negative and you bring it in, what happens to the negatives in the can? Yeah, they repel. So if I touch, I can remove them, leaving net positive. If this is positive, what does it do to the positives in the can? That side, I remove them, leaving it net negative. So charging by induction charges something up oppositely. Hence the cloud. The bottom of the cloud was negative. The ground becomes positive. Yes? Yeah, if I came in and touched this side, could I do it differently? This is where things get complicated, and I'm going to say, no, it still works the same way. The short answer is you can't think of all the negative electrons running to this side and leaving all the atoms over here. They kind of stay in place, but they kind of shift. The book draws some good pictures. They all just kind of shift, but they don't like, wee, wee. And so in reality, all the electrons aren't over here and all the positive over here. So it doesn't matter where you touch it. It'll still work. Good. Good review. All right, we're done with clickers. I brought this out to maybe better visualize the inverse square law. If you have a charge here at this point, you can think of the area as the force. This works with light, it works with gravity, and it works with charges. If you think of this as 1 unit square representing the force you'd feel at that point, so be it. You get twice the distance away, the force doesn't double or half. It goes down by a factor of 4. See how it spreads out to 4 unit squares? Kind of spreads out in a cone. And if you get 3 times as far away, the force will go down by a factor of 3 squared, 9. And you can see that there's 9 unit squares there. So maybe this will help you as a visual that the force decreases with the factor of square. Then it's not a linear thing. Hopefully that'll help. I don't know. Help some people, so I brought it out. Here's another fun one. You know, you're on a date and you want to impress your date. You can take a coin. We'll see if it works today. Find a level part of the table. That's the hardest part of this trick. There's a spot. I'm going to balance a match head on it, I hope. Oh. Put the glass over the top, and you bet your buddy, or try to impress your date, I don't know. And you say, can you knock the match off the coin without touching it, lifting it, or hitting the table? Basically, you can't make direct contact with it. And you guys being smart thinking, oh, we're in a unit having to do with electricity and charges. You might think you could do what? What's that? Induction. Induction. You remember the 2x4? I could move the 2x4 without even touching it if I brought a charge near it. The match head's probably pretty neutral right now, balance of positives and negatives, but I can polarize it. And what's neat is it goes through glass. The charge can. Let's see if this balloon has enough oomph in it to... It's getting sad. Let's separate some charges. Make this balloon positive. If I bring it near, it's going to polarize the match, I hope. And there'll be an attractive and repulsive force between the positives and negatives in there. Lame-o! Let's try the rod. Ta-da! What this means is I have not acquired enough charge to influence the match. And you know, I did this Monday before I used the balloon. We just didn't get to this part. So let's just try a fresh balloon, see if we can make it zestier. Woohoo! So, I would not have a second date. Oh well. Now it's a challenge, right? All right, let's see. Sometimes it just gets stuck. Wow. This works more often than it doesn't. Okay, you can see it influenced. And the glass does hinder it a bit. I bet this is too dirty. If I clean this. I'm serious. That's my guess, but I haven't cleaned it in many months. It should go through the glass, because what it does is it polarizes the glass also. And then the glass is charged. There's now a net charge on the inside of the glass, and that's what ends up influencing the match. And so usually it doesn't even seem like the glass is there. I'll clean the glass. We'll try it again next time. But hey, but you get the point anyway, I hope. Woo, and I balanced it really well. So here's a point. The more humid it is in the air, or the more you touch things and get it grimy and greasy, or from the oils in your fingers, those are conductive. And they can make charges go not where you want them to. So within electrostatics, the number one thing I have to make sure of is that something's clean and that it's not very humid. Otherwise, a lot of these demonstrations don't work. A second one is sharp points that we're going to get to for a lightning rod. But we have to discuss electric field first for that. But yeah, Utah, usually these demos work great because Utah's usually dry, nice and dry. And I'm a lot luckier than my colleagues at other universities where they have to keep them locked up and dry them out on purpose, or insert little heaters at the bottom of things to keep them dry, not as humid. So, there we go. Let's get into electric fields. Where are we at? Okay. An electric field. It's kind of sad, and I realized this from the get-go, but a lot of cool superhero powers could be with electricity and magnetism. Because an electric field is a force field around a charge. But, you know, this wouldn't make as much sense if we started out with it. But that's what an electric field is. It's a force field that kind of surrounds a charge and influences the space around it. A lot like a gravitational field. The Earth has mass, and so there's this gravitational field, and if we get in it, we're influenced by it. Our mass is. We're attracted to it. You guys produce a gravitational field because you have mass, and other masses are attracted to you. The more mass you have, the stronger the field. The more charge you have, the stronger the field, an electric field. But there's an analogy there. They're similar. It's a field surrounding the space. How we define it is if you have this charge and you get near it and you're charged, or you bring in some other charge, you know this now, you get influenced by it. There's a force between the charges, the Coulombs force. Now I can write it because we got the lights on. Two charges, distance, time, some constant. But it's proportional to the amount of charge and how far apart you are. So the electric field, we just call, it's the force per charge. Q being the charge. You put a charge in an electric field, it's going to feel a force. And that's how we define electric field. It's a force per charge. As an analogy, do you remember F equals ma? Newton's second law, acceleration. You want to make a mass accelerate? You exert a force on it? Well, let's put it in what we're used to, Earth. And let's deal with gravity, this gravitational field we're in. If we're in that gravitational field, we feel a force. Just rearrange that. This gravitational field, another way to think of it is a force per mass. You want that mass to accelerate, put it in a gravitational field. If you want this charge to accelerate, put it in an electric field. And it'll feel a force. This one's only attraction, where this one can be attraction or repulsion, because you can have two types of charges. Does that make sense? So the units of that are forces in newtons. And charges in coulombs, after Mr. Coulomb, Coulombs Law. What? E would be, that's what they use. They just call it newtons per coulomb. An electric field is a newton per coulomb. That's a force per charge. And this is going to come in handy, and we're going to get to another term where we deal with it per charge. Because these charges are small, we don't deal with them microscopically and individually, more macroscopically, overview, and it's a lot easier to deal with things per charge than look at all the individual ones. How does it look? If you have a positive charge, then the electric field goes away from it. So these lines represent the electric field. If you have a negative, they go towards. So an electric field has a direction. It goes from positives to negative. The convention is if you take a test charge, and the test charge is positive. That's how they define this. If you bring a positive charge near another positive charge, what happens to the test charge? Bring a positive test charge near this positive charge, and what happens to this test charge? Does it attract or repel? It repels. So that tells you which way the force is. You put that charge in an electric field, and it feels a force. It's accelerated. Which way? Well, they're the same charges repel. So it'll be out. Now I know the direction of the force field. If you bring it near a negative charge, it'll be attracted, and so the force will be towards it. They'll accelerate together. So your test charge is always positive, and that defines the direction of an electric field. So you can always remember which direction it goes. You can either just remember positives or negatives, or take your positive test charge and see what happens. Yeah? Oh, I got a charge, and let's call it positive. If I bring it near this one and place it in this guy's electric field, what's going to happen to him? He gets repelled. Now I know that the electric field is out. This is positive. That's positive. And we just discussed last lecture and the first half of this one that like charges repel. They have observed it. These are the laws we found out, and so I'm teaching and sharing it with you. They did this with the Millikan oil drop, but individual charges, I don't know if they ever actually have. But they've gotten it to really small quantities of it. But you can do it in a batch of positive charges, and they can see that if they're attached, I take a ping pong ball and charge it up positive, and I put it in an electric field, I see that it goes towards the negative side, not the positive side. And vice versa. If I bring it in near negatives, it goes towards them. It's attracted. So by convention, we say the electric field's in those directions. If you have two together, you can just connect them. You got electric fields like this. But the direction's the same. It goes from the positives to negatives. So if I take a little test positive charge here, I can tell where it's going to go. It's going to follow the electric field line. It's going to feel attraction to here and a repulsion from there. If I have two parallel plates, and this one's charged net positive, and that one net negative, then I know the electric field goes from positives to negatives. But there's an electric field on the outside too. It goes this way, and towards this one. And it starts bowing this way because it can kind of fly out. Whee! And you get something like that. So now if I take my test charge, I can always tell which way it's going to go. The Coulombic force it'll feel in this electric field. Yes? A little louder. I'm sorry, I can't hear you.
Sorry, is your test charge also going to emit in its own small electric?
Yeah, a test charge will have its own electric field, yes. But that's to help you, mainly it's to remind you like, oh, I don't remember what happens. Well, let's see, if I put a test positive in there, positives repel positives. Okay, it'll go that way. Positives attract to negatives. So it helps you figure out the direction of the electric field and what's going to happen. Did you have a question, James? Okay. So, let's do some. Volunteer! Who'd like to help us visualize electric fields today? Somebody with good hair. It's this classic demo. We're going to put your hand on here and charge you up. Come on down. This is called the Van de Graaff generator, and we're going to use it several times, I hope. The gist is there's a motor in the bottom attached to this pulley. All it does is rotate the pulley. If you come around here, we'll have you stand up on here, and I'll have you rest your hand on there.
Over here?
Yeah. All right, don't get too close. Put your hand on there. Is that comfortable? Mm-hmm. All right, don't step down, don't touch me, and don't let go. Okay. And you'll be, and then you won't get shocked that way. Okay. Yeah. So what's happening? We'll see what happens. Every time the belt comes off the pulley, charges separate because the belt likes them better than the pulley, different materials. They transport them up to the dome and they collect on the dome and start accumulating. She's touching the dome. She's a conductor. So some of the charge can transfer onto her. And it depends, everybody's hair is a little different. Some of it's getting up to her hair. Give us one of these and let's see if we can tell anything. It's starting to stand up a little. I didn't know if you wanted to undo your hair or not.
Do you want me to?
Can you do it one-handed? Where's it? It's snapping. I hear it snapping. It's working. See, we're getting there. Is that getting you or is that somewhere else? I hear it's shorting the ground. As long as it's not going through you, it doesn't hurt. So she has a lot of surface area, no offense, compared to the dome, and so it takes a bit of charge. But when the charge gets to her hair, it's the same charge. And same charges like to repel. I'm going to go ahead and turn it off. In order to repel that force, it's best if they stand up and spread apart. That's how they can get far enough away from each other. You can let go of the dome now. And as the charge bleeds off of her to the water vapor in the air, she becomes neutral again. Not quite, but you can step down. Yeah, you heard that, didn't you? Cool. It worked. Thanks. Give her a hand. Let's see, let's put this hairnet on here. So her hair was actually represented the electric field lines. Let me get that going. Take a bit. And so if that becomes charged all negative, let's say, it's like one big negative charge, and the field line should be pointing towards it. And so if you threw a negative ping pong ball in the air, it would repel. And if you threw a positive one, it would attract. These yarn will get charged up. And then they get stuck, of course. We'll let that go for a while. See what happens. You can see it starting to happen. As the charges get moved onto the yarn, they get repelled because they're the same charge. To help you visualize an electric field anyway. The next class will continue with how you can shield yourself from an electric field. I'll show you how a lightning rod works. These sharp points are the other nemesis that I have to worry about. If you want charge to build up and you have a sharp point, that changes and influences the electric field, a lot like shielding can. And it'll allow charge to flow where you don't want it to. Let's see. Her hair worked better than this, didn't it? But you get the idea. Yeah, these are heavier than hair. And these will slowly keep charging up. We'll revisit this more and finish this chapter next time. We'll leak over a little before we get to circuits. Do you guys have any questions? You're also welcome to come get your stuff if you weren't here at the beginning and ask me what the heck was going on if you don't know why they're up here. Yeah, come on up, Kate, and ask me.